And in particular, we saw we can generalize the thermodynamic identity if we, for example, consider the internal energy to be a function of entropy and volume and particle number. And I can write du is tau d sigma minus pdB, what we had before, plus the term involving flow of particles, mu dn. So one way of defining what we mean by chemical potential, this identity tells us, is if I consider entropy and volume to be fixed, chemical potential is derivative of internal energy with respect to number of particles. I could also consider changing the entropy if I think of the entropy as a function of the other variables, u, v, and n. Then this identity tells me that the chemical potential can be written as minus temperature derivative of entropy with respect to number of particles with internal energy and volume fixed. And we also saw that if we consider holding the temperature fixed, then if we differentiate Helmholtz free energy with respect to number of particles with temperature and volume fixed, that's the chemical potential. In the case of the classical ideal gas, the low-density ideal gas, we saw the chemical potential can be written as tau times natural logarithm of concentration divided by quantum concentration. That's in the regime where concentration is small compared to quantum concentration. Then we talked about the situation in which a system is in contact with a large reservoir. The reservoir has some specified chemical potential and temperature. And then we asked, if we look at some particular state of the system, characterized by a number of particles n and energy epsilon, what's the probability for the system being in that state? And we said it's proportional to the Gibbs factor, which is e to the n times chemical potential minus energy divided by temperature. To normalize that, we divide by a term called the Gibbs sum, which is the sum over all states of the system, e to the number of particles in the state times chemical potential minus energy of the state divided by temperature. That's called the Gibbs sum. And this is the Gibbs factor. Now the reason, well, there are a lot of reasons for talking about chemical potential, but we're going to use it in particular in the following context. So far we've talked about the classical ideal gas. We want to go on to the case where the concentration is not necessarily small and quantum effects start to become important. Then there are some qualitatively new effects that we'd like to understand. So one of our reasons for introducing the chemical potential so that we can study ideal gases in the quantum regime. It's a very good mathematical tool for making that study easier. So remember, we want to consider indistinguishable particles. We learned our lesson when we studied the classical ideal gas. So one way of thinking about that is we have an ideal gas. That means there's no interactions among the particles. So we can consider the single particle orbitals So if we can imagine the system just had one particle, there's a ground state, a first excited state, second excited state, and so on. Okay? And if we put many particles in the system, if the particles are non-interacting, that means the total energy will just be the sum over orbitals, I'll use A to label the orbitals, the number of particles in orbital A times the energy of that orbital. Okay. So that captures the idea that the particles are non-interacting. The energy cost of adding a particle in a particular orbital doesn't depend on what other particles are already around or what the number of particles occupying that particular orbital is. That's the sense in which the gas is ideal. So when we sum over configurations, what we're interested in is how many particles are in the ground orbital and how many are in the first excited orbital and so on. And summing over configurations will mean summing over the occupation numbers of each one of the orbitals. Okay? And that's how we can keep track of what the different states of the system are. Okay, except there's something interesting now that we have to discuss, which is that there are two different types of indistinguishable particles. Well, just to explain briefly the connection with the chemical potential, which we'll come back to and discuss in more detail, the chemical potential is going to be helpful because we have some fixed chemical potential for the system, and then we can determine the probability distribution for this occupation number orbital by orbital for some fixed chemical potential. And then with that fixed chemical potential, there will be some expected number of particles in the system, and so we'll be able to study the properties of the system with a specified number of particles by adjusting the chemical potential so we get that number of particles. Okay. Well, we'll be seeing that in more detail. Anyway, the two types of indistinguishable particles are fermions and bosons. For bosons, for a particular orbital, the occupation number of the orbital can be any non-negative integer. It can be empty, it could have a single particle, 2 particles, 3, etc., up to an arbitrarily large number. For fermions, there are only two possibilities. Either the orbital is empty or it's occupied. Once it's occupied, no further particles can be added to that orbital. So that is called the Pauli exclusion principle for fermions. Give me an example of a fermion. An electron is a fermion. Example of a boson. A photon is a boson. Of course, we've already talked about distribution functions for photons. Yeah. That's right. But they have two different spin states. So it's really just a question of terminology. When I speak of orbital, I mean completely characterizing all the quantum numbers of the state. So spin up and spin down, in the language I'm using here, would be two different orbitals. Okay? Another example of a boson is a helium atom. Well, if it's helium-4 anyway. The photon, well, it's kind of a special case. We've already discussed it in connection with the Planck distribution, in that there really is no conserved photon number, as we discussed. If you have a cavity, you heat it up, the number of photons in the cavity can keep growing as the temperature increases. But we'll often be interested in the case, like for a helium gas, where we have some fixed number of particles, the particle number is conserved, and then we can speak of a chemical potential, which controls the number of particles in the system. And so what we'd like to understand is a gas of bosons with a conserved particle number, which we haven't yet discussed. We only talked about the case of photons. Now, there's another way of characterizing the difference between bosons and fermions. You learned, I think, at the end of Physics 12b a little bit about angular momentum, right? True? And commutation relations of Jx, Jy, and Jz and all that. So you know that if you consider a quantum state, you can consider rotating it about some axis. Let's say rotating it by angle theta about some axis in space n hat. And then there will be some unitary transformation that represents that rotation, which describes the effect on the quantum states of the rotation. Okay? So that state vector under the rotation will be replaced by a new state vector given by a unitary transformation that depends on the axis of rotation and the angle of rotation times the initial state. And what you probably also learned is that we can write this unitary in terms of the angular momentum, that it's the exponential of minus I, the angle theta, n hat dot angular momentum divided by h bar. Does that sound familiar? Okay. So you, I guess, learned about how angular momentum is quantized, and you know that if I consider angular momentum along some axis, for example, the z-axis, that in units of h bar, it can be 1/2 times either an even integer or an odd integer. A particle which has angular momentum which is an integer multiple of h bar is a boson. If it's 1/2 of an odd integer, or integer plus 1/2, then it's a fermion. So one way of appreciating the difference is to consider the effect of taking our particle and rotating it by 2 pi, okay, which should have the effect of doing nothing, because a rotation by 2 pi brings it back to its original configuration. But if I consider how this unitary transformation behaves when theta is 2 pi, n hat dot j, depending on whether it's a fermion or a boson, is going to either be an integer or an integer plus 1/2. Okay? So that means that r, about any axis when we rotate by 2 pi, will be, e to the I 2 pi times integer for a boson, or e to the I pi times integer plus 1/2 for a fermion. So this is 1, or in other words, the identity operator, and this is minus 1, e to the I pi, which is minus 1. In the case of a boson, in other words, the effect of rotating by 2 pi is nothing. It's just the identity operator. In the case of a fermion, the state vector changes sign. Question? Say again? Oh, okay. Thanks. Right, so it's e to the I 2 pi times integer plus 1/2, or in other words, e to the I pi, which is minus 1. Thank you. Well, it sounds kind of funny that rotating something by 2 pi could change its wave function. Well, it only changes it by a minus sign, and as you remember, it's only the state vector up to a phase which has a physical meaning. Even so, it's funny. So why is it that rotating by 2 pi should somehow be distinguishable from doing nothing at all? Well, there's a trick for demonstrating this. Traditionally, it's done with a coffee cup. but I don't have one, so I'm going to use an eraser. And the right way to do it is with a coffee cup which is filled with coffee, but I don't recommend that for beginners. So I have an eraser. I'm going to rotate it by 2 pi. Here we go. That's pi. And now I've rotated by 2 pi, and the eraser is back to where it started. But is everything back the way it started? My arm is messed up, and I'm in enormous pain. So what I really want to do is to rotate back to get back where I started. But resisting every impulse in my body, which tells me to do that, let us suppose that I continue to rotate by another 2 pi, and I bring the eraser again back to its original configuration, and my arm has become untwisted. Okay? So it's really only when we rotate by 4 pi that we have a transformation which leaves everything unchanged, both the eraser and my arm. For bosons, bosons don't care that my arm is twisted, and fermions keep track of whether it's twisted or not with the minus sign. Now, there's another way of characterizing the difference between bosons and fermions, which is we consider 2 particles, let's say initially at positions x1 and x2. They're indistinguishable particles, but of course I can distinguish the 2 positions. I know there's a particle at x1 and one at x2. Let's say they're 2 electrons or 2 helium atoms. But then I can consider exchanging them, slowly moving this particle to position x1 and this particle to position x2. I'll call that an exchange. And it takes a quantum state with particles at positions x1 and x2 to another quantum state with particles at those 2 positions. That, too, I can think of as some transformation on state vectors. So it's represented by an operator. I'll write it as script r, the exchange operator. Now, suppose I apply the exchange twice. So I do the exchange, and then I do it again. Okay. So now I've really returned the particles their original configurations. And so that should be the same thing as doing nothing at all, the identity. Okay. 2 exchanges, it's the same thing as not exchanging at all, right? So r squared is equal to the identity, but r itself can have 2 different eigenvalues. The eigenvalues have modulus 1 because it's a unitary operator. They have to square to 1. So r can have the eigenvalues squared are equal to 1, but the eigenvalue of r can be either plus 1 or minus 1. If it's plus 1, that means when you exchange 2 indistinguishable particles, nothing happens to the wave function. That's the case of bosons. If it's minus 1, you take 2 indistinguishable particles and exchange them, but the wave function changes sign under the exchange. That's the case of fermions. So another way of saying it is, if I think of the wave function as depending on the positions of 2 particles, in the case of a boson, the wave function is a symmetric function of the positions. So if I swap x1 and x2, it has the same value. So we say in that case it's a symmetric wave function, symmetric under exchange of the 2 particles. If it's a fermion, if I swap the positions of the 2 particles, it doesn't leave the wave function invariant, it changes its sign. So it has to be an antisymmetric function of the positions x1 and x2, antisymmetric under exchange. And in fact, we can understand the origin of the Pauli exclusion principle from this point of view. suppose we have two orbitals and they're each occupied by one particle. In the case of non-interacting particles, the wave function as a function of the positions of the two particles just factors into a wave function for the first particle and a wave function for the second. So I could write it as the wave function in orbital 1 as a function of position x1 times the wave function for orbital 2 as a function of position x2. Okay, except that's not symmetric or antisymmetric. If they're bosons, I should make it symmetric by adding the same function but with x1 and x2 interchanged. Or equivalently interchanging A and B. So that would be the symmetric wave function, which would be the right way of writing the two-particle wave function for a boson, or pair of bosons. In the case of fermions, though, I would have to put in a minus sign. So now it's antisymmetric when we interchange x1 and x2. That's the appropriate form for two fermions. But if A and B are the same orbital, if A equals B, then, of course, this would vanish. So we can't have double occupancy in a single orbital because we can't write down an antisymmetric wave function if both functions, if both indistinguishable particles are in the same orbital. Okay. So that means from the antisymmetry of the wave function, we obtain the Pauli exclusion principle. Two particles, fermions that is, cannot occupy the same orbital. No double occupancy. Now, why should it be that these two things are related? That what happens to an electron when we rotate it by 2 pi has something to do with what happens when we take two electrons and we exchange them. Feynman used to love it when people would ask him this question. Uh-oh, I'm going to have to take off some of my paraphernalia. Because he would always respond by taking off his belt. He would say, well, it's like this, except he had the Brooklyn accent, which I can't really imitate right. He would say, look at my belt. Okay? So think of the two ends of the belt as two electrons. Okay? Look at my belt. It's all nice and straight. Now I'm going to exchange the two particles, the two ends of the belt. Okay? So now the particles are in the original position. The two ends of the belt are in the same place as before. But what about the belt? Well, if we stretch it tight, we can see that the belt now has a twist in it. The belt has a 2 pi twist. So if we wanted to get rid of the twist in the belt, what would we have to do? Well, we could take one of the particles and rotate it by 2 pi. So if we want to keep the positions of the particles the same as they were originally, and we don't want the belt to have a twist, we do the exchange and then rotate one of the particles by 2 pi. So that should leave the wave function invariant, but the exchange by itself, or the rotation by itself, need not. This is an example of what we call the connection between spin and statistics, Feynman would say, as he puts his belt back on, because he was pretty skinny and sometimes he was at risk of his pants falling down, but I'm not too worried about that. Nevertheless, we'll take a pause while I get the twist out of my belt. Damn it. You probably think I did that on purpose, but no. The danger of exchanging things, and then you get twisted. So I can try to explain this a little better. Or, well, I don't know, maybe it's a mistake to try. Try the bell trick at home, and show it to your friends. They'll be impressed, and you can say, this is the connection between spin and statistics. Okay. So there's a connection, we say, between spin and statistics. By statistics, well, why is it called statistics? We're going to do statistical mechanics for bosons and fermions, and we'll see that they're different. So statistics means symmetric or antisymmetric under exchange. And spin, well, the important distinction for spin, the intrinsic angular momentum of a particle, is whether you get a plus or a minus 1 under rotation by 2 pi. So why is it that two particles are connected by a belt? You probably didn't know that every two electrons in the universe are connected by belts, which can get twisted. We can think about the belt in the following way. There's one other ingredient that we need to understand why there's a connection between spin and statistics. Why does rotating by 2 pi have something to do with exchanging two particles? The other ingredient we need is the existence of antiparticles. So let me think about drawing world lines in space-time. I have time going up. And here's a particle. I'll draw it with an arrow going forward. It's moving forward with time. And so if it's an electron, it's carrying electric charge forward in time, so to speak. That's a particle. But you can think of an antiparticle, at least impressionistically, as a particle, but it's going backward in time. It has the opposite value of all of the quantum numbers. Well, not the mass, but the charge in particular. So the antiparticle of electron, a positron, has charge +1 instead of -1. And we can think of carrying charge -1 backward in time as being equivalent to carrying charge +1 forward in time. Now, the process of exchange looks like two crossed world lines like this for two particles. So that represents an exchange of two particles. They've changed places as a function of time. And there's either a +1 or a -1 associated with that exchange, depending on whether they're bosons or fermions. What does that have to do with rotating one particle by 2 pi? Well, there's one other idea, which is because of the existence of antiparticles, we can consider particles being created in pairs or annihilating in pairs, where a particle and an antiparticle meet and annihilate or get created together. And in my space-time diagrams, pair creation looks like this, where I create a particle and an antiparticle. It takes some energy to do that, but I don't need any electrical charge because the electron and positron have opposite values of charges or any other conserved quantities that they carry. So that's pair creation. And pair annihilation looks like that, where the electron and positron, or particle and antiparticle, come together, annihilate one another, and disappear. The energy gets transformed into some other form. Maybe it gets taken away by photons or something. But the electron and positron are gone when they annihilate. So now, if you can think about a diagram like this. So what it means is, here I created a particle and an antiparticle. Here a particle was coming along. Then that antiparticle annihilated the particle that was coming in, and the particle that was created when I created the particle-antiparticle pair then continues. And this process, if this creation and annihilation are very close to one another, you can't really tell them apart because this particle that was created annihilated, tiny instant later. And so whether it was ever there or not, you would have to have very excellent time resolution to see. So these things, for all practical purposes, are really the same, even though here I created a particle and then annihilated it. So you should think of these as something that can be smoothly related to one another. Okay. So now I consider this exchange process that I drew before, and I imagine deforming it to a process that looks like this. Okay, which I was able to do by deforming a particle going forward in time to this process in which there was a pair creation followed shortly after by a pair annihilation. But then I can let the pair creation and annihilation get further and further apart from one another and get a process like this in which a pair was created here, annihilated here, created here, and annihilated there. And you can see how I could smoothly bend the lines to change this process to this one. Okay, now one more smooth change. Here, I have two particles which annihilate one another, and then an instant later, two particles, or a particle and antiparticle, are created. So you can't really tell the difference between that and the case when they didn't really annihilate at all. Right? They annihilate, and then less than a nanosecond later, a new pair is created. Well, why don't we just deform that to a process in which the lines connect the other way, like this. Okay, and now I can straighten out these world lines. So I get something that looks like this, except for one thing. This world line's got a twist in it. So when I straighten it out, it's actually going to look like my belt. It's going to twist by 2 pi as it goes forward in time. Okay? So I claim that the process in which the two indistinguishable particles are exchanged really can be smoothly changed to the process in which there is no exchange. Both particles wind up where they were to begin with, but one of them has been rotated by 2 pi. And that's why the two things are related. If there's a plus or minus sign, depending on whether they're fermions or bosons associated with exchange, that plus can't change to a minus suddenly. It would have to jump. But if we make all these changes continuously, if it's a minus 1 to begin with, it's going to have to be a minus 1 at the end of the smooth changes. If it's a plus 1 to begin with, it's going to have to be a plus 1 at the end. So if there's a minus 1 associated with exchange, there also has to be a minus 1 associated with rotation by 2 pi, twisting the belt. That's the argument. And you see that we really needed the existence of antiparticles to establish that kind of connection between spin and statistics. All right, so that was just for cultural enrichment. Okay, now, how are we going to use this stuff? Well, I already kind of told you. We want to understand quantum gases. So we want to consider the case in which we have many orbitals, each of which can have some occupation number. If they're bosons, the occupation number can be any non-negative integer. If they're fermions, it can only be 0 or 1. And we'd like to see how the number of particles in an orbital on the average depends on the temperature and the chemical potential. That's what the Gibbs sum tells us about. So consider fermions, first of all. And look at one orbital. It has energy E. And it can either be empty or occupied. So either n is equal to 0, it's empty, or n equals 1. Those are the only possibilities for fermions for a single orbital. So the energy is either 0 if there's no particle there, or it's the energy of the orbital if the orbital is occupied. So if I consider the Gibbs sum for just that single orbital, it's equal to 1 when it's empty, or e to the, well, n mu minus e over tau, if it's occupied, but e, in this case, n is equal to 1, and e is equal to e when it's occupied. So it's just 1 plus e to the mu minus e over tau. That's the Gibbs sum. So the probability of being empty is the Gibbs factor, which when n equals 0 and e equals 0 is just 1, divided by the Gibbs sum. And the probability of being occupied, the occupation number being 1, is the Gibbs factor times 1 over the Gibbs sum. And the expectation value of n, which is in general, it's just the sum of n times the probability of n. Well, in this case, n is either 0 or 1. So it's just equal to the probability of having n equals 1, the orbital being occupied. And that's this expression. If I divide numerator and denominator by e to the mu minus e over tau, I can also write the expectation value for the occupation number of the orbital as 1 over e to the energy minus chemical potential divided by tau plus 1. So actually I'm going to call that f of e. It's some function of the energy of the orbital that depends on the chemical potential and the temperature. And that is called the Fermi-Dirac distribution. Why is it called a distribution if it's just the expectation value of the number of particles in an orbital? Well, for the same reason we spoke of the Planck distribution, because we're going to be interested in the case where there are many orbitals, and this is going to tell us how the total particle number will be distributed among the orbitals. Right? The chemical potential is fixed. It's the same for all the orbitals. As the energy of the orbital varies, the occupation number, the mean number of particles in that orbital, is going to depend on its energy, as described by the Fermi-Dirac distribution. So if we draw what that function looks like, when the chemical potential matches the energy, when the energy is equal to the chemical potential, then the mean number of particles is 1/2. We call that half occupancy. The probability is 1/2 that the particle is occupied. When the energy is small compared to the chemical potential, it approaches 1. The low energy orbitals are occupied with a probability close to 1, so the expectation value for the occupancy is 1, and then it falls off exponentially over here. So we say the orbital is half filled when the energy is equal to the chemical potential. So this function, it looks kind of like a hyperbolic tangent, except displaced vertically. In fact, with a little algebra, you can see 1 over e to the x plus 1, which is what we have, where x is equal to e minus mu over tau, is the same thing as 1/2 1 minus hyperbolic tangent x over 2. Well, the hyperbolic tangent goes to minus 1 when x is large and negative, so this becomes 1, that's over here, and it gets exponentially close to plus 1 when x is large and positive. That's this exponential decay over here. Now, if we let the temperature get very small, then the step from up here, where the occupation number is nearly 1, to down here, where it's nearly 0, becomes very sharp. And it occurs right at the chemical potential, so it'll look something like that. As the temperature goes to 0, with the orbitals which have energy below the chemical potential occupied with probability very close to 1, and those with energy above the chemical potential occupied with probability very close to 0. So when we go to 0 temperature, the system is in its quantum mechanical ground state. It doesn't have any thermal fluctuations. So this is the ground state, the lowest energy state for a system with some specified number of particles. Well, what is n? The number of particles. So we got a bunch of orbitals, and then the chemical potential is here, say. For the Fermi-Dirac distribution, as the temperature goes to 0, if this is energy going up, all of the orbitals with energy below the chemical potential are singly occupied with probability 1, and all the ones with energy above the chemical potential are empty. That's the lowest energy state with that specified number of particles. If we have n particles, what's the lowest energy state we can make? Well, first we put a particle in the lowest energy orbital, but now that's occupied. We can't put another one there. Then we put the next particle in the next orbital, and so on, until the bottom n orbitals are all occupied and the rest are empty. That's the lowest energy state with n particles. And so that tells us that the chemical potential, if we want to have exactly n particles, has to be placed in between the energy of the nth orbital and the n plus first orbital. Okay, that's how the chemical potential and particle number are related in the 0 temperature case. Okay, well, what if they are bosons? So now, single orbital again. It has energy E, but it can be empty, or it can have 1 particle, or it can have 2, and so on. Any non-negative integer. So if there are n particles occupying that orbital, the energy is n times the energy of the orbital. The Gibbs sum is now going to be the sum from occupation number 0 to infinity of the Gibbs factor, e to the number of particles mu, minus the energy E over tau, but now E is n times the energy of the orbital. So it's the sum of, I guess I can write it as the, e to the n, mu minus E, now little e for the energy of the orbital divided by tau. So it's just a geometric series when I sum from 0 to infinity. The sum of x to the n is 1 over 1 minus x, when n is summed from 0 to infinity, at least if x is less than 1. So then I can write this as 1 over 1 minus e to the mu minus e over tau. But for that, in order for the sum to actually converge, the chemical potential better be below the energy of the orbital. Okay? So that this is a sum of the nth power of some number less than 1. So mu minus e is negative, in other words. Now, what is the expectation value for the particle number? So now our distribution function, the expectation value for the number of particles, which depends on, the energy, but also on the chemical potential and the temperature, will be 1 over z, the sum of n times the probability, which will be the Gibbs factor, e to the mu minus epsilon over tau, divided by script z. And it's convenient to notice that if I define lambda as e to the mu over tau, so what appears in the exponential is lambda to the nth power. Lambda itself is a useful quantity, so we'll give it a name. We'll call it the activity, or absolute activity. It's just e to the mu over tau. If we differentiate with respect to lambda, we bring down a power of n. If we differentiate under the sum, the Gibbs sum z, so I can write the expected number of particles in the orbital as 1 over z, from this normalizing 1 over z, and then lambda dd lambda of z. When I differentiate with respect to lambda, then lambda to the n becomes n lambda to the n minus 1, and then I multiply by lambda to get it back to lambda to the n. The Gibbs sum itself, which was over here, if I write it in terms of lambda, is 1 over 1 minus lambda e to the minus epsilon over tau. So if I differentiate that with respect to lambda, then there's a minus sign here, and also this is in the denominator, so that gives two minus signs. So I get an e to the minus epsilon over tau in the numerator. Then the denominator gets squared. But when I divide by z, dividing by z gets rid of one of the factors in the denominator. And then I have to multiply by lambda. So this is lambda e to the minus epsilon over tau divided by 1 power of 1 minus lambda e to the minus epsilon over tau. Or, writing again what lambda is, and dividing numerator and denominator by e to the mu minus e over tau, it's 1 over e to the e minus mu over tau minus 1. That's not z, that's equal to f of e. And that is the Bose-Einstein distribution. It tells us how the mean occupation number of an orbital with energy E depends on the chemical potential and the temperature. So again, same interpretation. If I have many orbitals, then I have the same chemical potential for all, but they have different values of the energy. And this is called a distribution function because it tells me how the mean number of particles in the orbital depends on its energy. And it looks just like the Fermi-Dirac distribution, except for what? Yeah, there's this very important sign in the denominator. In the distribution function, it will be plus or minus 1. And the plus will be for fermions, and the minus for bosons. Kind of confusing because everywhere else so far I've talked about minus signs for fermions and plus signs for bosons, but this time it's the other way around. Don't get confused about that. So if I come back to my picture, this was the Fermi-Dirac distribution. The Bose distribution, the Bose-Einstein distribution, will look similar when the occupation number is small, because when the occupation number is small, that means the exponential is much more important than the plus or minus 1, right? And when the exponential gets really big, since the exponential is in the denominator, the distribution, whether it's Fermi-Dirac or Bose-Einstein, is decaying exponentially as the energy increases. But in the case of Bose-Einstein, as the energy approaches the chemical potential, it starts to take off. So Bose-Einstein and Fermi-Dirac deviate from one another substantially when the energy becomes comparable to the chemical potential, though when the energy is high, they track one another closely. So in fact, all the stuff we said earlier about the classical regime we can recover in this language. The classical regime, that's the case in which the occupation number is low. Remember, we said it was classical if the number of orbitals was really large compared to the number of particles, so we didn't have to worry about double occupancy. That's the case in which the expectation value of the number of particles in a typical orbital is really small compared to 1. That means there will be a large probability there are no particles in the orbital at all, a small probability that there's a single particle, and a negligibly small particle that there's a probability that there's 2 or more particles. Okay? So that's the classical regime. And in the classical regime, where f of e is small, that's where the difference between fermions and bosons becomes invisible, because the two distribution functions look the same. The distribution function becomes dominated, like I said, by the exponential. Who cares about the plus or minus 1? So it becomes 1 over that exponential, or the distribution function can be approximated by e to the mu minus e over tau. Or if you want to write it in terms of the activity, it's the activity lambda times the Boltzmann factor e to the minus e over tau. So in that case, this distribution function, remember, means the expected number of particles in the orbital, and it's really small. Particle is most likely empty with small probability. It has a single particle in it and almost never has more than one particle. Therefore, the difference between fermions and bosons doesn't matter in that regime. Right. So I keep saying we're doing this stuff because we want to understand the quantum ideal gases, and I really meant it. But it's not true, because I'm going to talk again about the classical ideal gas, just so we can see how in this formalism we can recover what we found earlier when we studied the classical gas, or in other words, the ideal gas in the classical regime, the low density regime. Here we go again. Well, now I want to consider the total number of particles by summing over the orbitals and summing up the expected number of particles in each orbital, right? So this will be the expected number for the total. So now I sum over orbitals and give the expected number of particles in that orbital to find the expectation value for the total number of particles. So we know now that that's the sum over orbitals. The activity lambda, which doesn't depend on the orbital, just on the chemical potential and the temperature, so I can actually take that outside the sum, times e to the minus the energy of the orbital divided by tau. That's because we're in the classical regime, and I'm using the classical form of the distribution function that applies at low density. So maybe I should write approximately equal because we're in the classical regime. Now it doesn't matter anymore if they're fermions or bosons because double occupancy almost never happens. Well, guess what? We've done this sum already. We did the sum over orbitals of e to the minus e over tau because when I first introduced the Boltzmann factor, I guess the first calculation we did was a single particle gas. And a single particle summing over states is just the same thing as summing over all the orbitals that that particle could be in, right? So we've done this sum already. And I'll just remind you what we found. We called it Z1, the partition function for the single molecule gas. It was equal to the volume times the quantum concentration. That's how the quantum concentration came into our lives, and it's been haunting us ever since. Right, so for the total number of particles, it's the same sum except there's a factor of lambda. So the total number of particles has an expectation value, which is lambda times the single molecule partition function, which is lambda quantum concentration times volume. And of course, if you want, we can regard that as an equation for lambda. Now remember, now we're talking about a big box, lots of orbitals. So fluctuations around the mean value, although they do occur, because since we fix the chemical potential, we're imagining that our system is in contact with the reservoir, diffusive contact. So particles can flow back and forth between the system and the reservoir. And the system finds its most probable configuration where it has some number of particles such that its chemical potential matches that of the reservoir, right? But those fluctuations aren't very important because it's a big system. The usual argument, when we have a very large system, the expectation values about mean values aren't important. So we just have a gas with some number of particles and this mean value that we've computed. And so you can think of this as a formula for the activity. The activity, which means e to the mu over tau, where mu is the chemical potential, is the number of particles divided by the volume times 1 over the quantum concentration. The concentration is number of particles divided by the volume. So that's concentration divided by quantum concentration. So I could take logs of both sides and multiply by tau and get a formula for the chemical potential. The chemical potential is tau log of concentration divided by quantum concentration. Well, that's a formula that we saw before. We derived it before by first deriving the free energy, right? And then we had to fix an error at first we hadn't taken into account that the particles were indistinguishable, so we had to divide by n factorial in the partition function. And when we did that, we got a free energy from which we could obtain the chemical potential, and we got this formula. Because the chemical potential is the derivative of the free energy with respect to the number of particles at fixed temperature and volume. So before we had to put in that correction for the indistinguishability of the particles by hand. We added that 1 over n factorial to the partition function. But here, that's all been taken care of for us by the Fermi-Dirac or Bose-Einstein distribution. Of course, they're the same thing in the classical regime. Because now we're summing over the orbitals and keeping track of how many particles are in each orbital, and that completely characterizes the configuration. It's not that the particles have names, Alice, Bob, Charlie, and Alice is in orbital 1 and Bob is in orbital 7. All we care about is how many particles are in each orbital. Then we summed over orbitals and got the number of particles, and then we were able to invert that to find the chemical potential, and we got the formula that we had obtained earlier. Now, if I wanted to go from here to get the free energy, I could just integrate the chemical potential. That would be one way of doing it. So if this expression is the derivative of the free energy with respect to particle number, I can just integrate that to find the free energy. When maybe I should write it as, just to make sure it's clear, tau times natural log of number of particles minus log of volume times quantum concentration. So the only part that depends on n is this log n. So when I integrate it, I can write the integral as the integral of log n times tau, which is n log n minus n. And then this just becomes this constant times n, so I have minus n times log v times quantum concentration. And then in principle, there's some constant of integration. I could do that because I was obtain the free energy, or the relation between chemical potential and free energy holding temperature and volume fixed. So if temperature and volume fixed, this is just a constant. So if I integrated is the integral dn of mu holding temperature and volume fixed. Mm-hmm. And then if I put the factors together again, I can write this as n times temperature times log concentration divided by quantum concentration minus 1. And I can drop the constant if we define the free energy. There's some zero of free energy which I can shift, but if I say the free energy is 0 when the number of particles is 0, then I can choose the constant to be 0. And that agrees with the formula we had before. Okay. So, well, as long as we're talking about classical ideal gases again, let's talk about classical ideal gases and say a little bit about their thermodynamic properties. You've probably seen this before, but that's okay. It's good to recall. The next time I really will. Well, no, maybe I won't. I better not say that. let's consider the thermodynamics of an ideal gas, and in particular, what happens to an ideal gas when we make reversible changes. The thermodynamics of the classical ideal gas. Let's imagine, first of all, a gas that undergoes isothermal expansion. So we have a gas in a chamber, but one of the walls is a movable piston, and we can allow it slowly to withdraw so that the gas expands. We put the gas in contact with a reservoir at temperature tau. It's in thermal contact, so heat can flow from reservoir to gas or from gas to reservoir. We're going to do it slowly, so we stay in the most probable configuration at all times. Consider reversible. We're doing it slowly. Isothermal, because we're in contact with a reservoir at fixed temperature tau. Expansion. So the final volume, well, I'll call that VF. We start out with some initial volume, VI. It's an ideal gas. We know pressure volume is equal to number of particles times temperature. We also know its entropy, which we could, in fact, I think we already did in an earlier lecture, derive the entropy from the free energy. But I'll remind you that it's number of particles times log quantum concentration volume divided by number of particles plus a number, which is 5/2, multiplying the n. Okay. So the temperature is going to be fixed because it's isothermal. The number of particles is fixed because I'm not letting any additional particles enter the chamber or be removed from the chamber. So the pressure and the volume are inversely related. The final volume, PF, divided by the the final pressure divided by the initial pressure is equal to the initial volume divided by the final volume. If the gas expands, the pressure goes down. And since the temperature is fixed, the quantum concentration is fixed, the number of particles is fixed, the only thing that's changing is the volume, so that tells us how the entropy changes. Since the entropy goes like the log of the volume, it's the difference between the final and the initial entropy, which is given by n times the log of the ratio of final volume divided by initial volume. So when the gas expands, the entropy goes up. Makes sense. It has more accessible states. When there's more volume, there are more places for the gas molecules to be. More states, higher entropy. Now we can calculate the work done during the expansion. It's just the integral of pressure times change in volume. And because the ideal gas law at a fixed temperature and particle number holds at all times, during this reversible expansion, we integrate from the initial to final volume, and the pressure, according to the ideal gas law, is number of particles times temperature divided by volume, integrated dV. So the integral is just a logarithm, and this is equal to n times temperature times log of final volume over initial volume. So you can see there's a relationship, a simple relationship between the work done and the change in the entropy. The work is the temperature, which is fixed, everything is isothermal, times the change in the entropy. Now why does that make sense? Okay, well there was some work done the system did work when it expanded. So there was some energy expended by the system. Where did it come from? Where did all that energy come from? Well, so I'm holding the piston and slowly releasing it. The system is pushing against the piston. So it's doing work on me, right? The energy to do that work has to come from somewhere. Where is it coming from? It's coming from the reservoir, right? Because we're in thermal contact with the reservoir. The reservoir has a fixed temperature. And so heat has to flow in from the reservoir to the system. And this change in the entropy is just keeping track of the heat flow. Remember, the thermodynamic identity, in this case with number of particles fixed, says change in internal energy is equal to tau d sigma a minus p dv, where we can think of this as the work done and this as the heat flow. We can integrate both sides of the equation. Now, what about the internal energy? How does it change during this process? It doesn't change, right? Because the ideal gas law holds at all times. And the internal energy of an ideal gas is 3/2 m tau, right? Temperature stays the same. Particle number stays the same. So this is a constant during the change. So this is equal to 0. No change in the internal energy. So the heat flow into the system has to match the work done by the system. And that's why we found that tau times the change in entropy is equal to the work done. So this is just conservation of energy. The first law of thermodynamics I can write as the change in internal energy in general is equal to, I'll call it dq minus dw. We have to be careful about the minus signs, which can be very confusing. Here by dq, I mean the heat flow into system. In this case, it's coming from our reservoir. Heat flow into the system can increase the internal energy of the system. And by dw, I mean work done by system. The work done by the system can deplete its internal energy. That's why there's a minus sign in front of the dw. But it's just conservation of energy. Change in energy of the system is the heat flow in minus the work the system does. And it's also dignified by the name of the first law of thermodynamics. What was that? And let's talk about another type of reversible change. Reversible isentropic expansion. Now, same picture. We've got a gas in a box, and it has a movable wall. But now I'm going to thermally isolate the system. It's not in contact with the reservoir. It's well insulated. No heat flow in or out. Again, we're going to have the initial volume VI expand to become the final volume VF. Okay. But now, there's no heat flow. So that means, and this is why it's called isentropic, dq is 0. In this reversible change, the entropy is fixed. And we talked before about how when you make a small change in a closed system, it doesn't change the entropy. That's what we're talking about here. No contact with the reservoir. It's a closed system. Change it slowly. The entropy stays the same. No heat flow in or out. Now again, if we look at our expression for the entropy, we can see what that implies about what happens to the temperature and pressure. So since the entropy of our classical ideal gas can be written as n times log, and now I'll make use of the fact that the quantum concentration goes like temperature to the 3/2 power. And the expression for the entropy that I have over here has a log of the quantum concentration in it. And it's got some numerical constants, but they're just constants. So I can write the entropy as natural log of volume times temperature to the 3/2 divided by number of particles plus a constant. And that's going to be fixed. Number of particles is also fixed. So if the entropy is unchanged, then what else is unchanged? Well, how is the volume related to the temperature? We'll have to have volume times temperature to the 3/2 equal a constant for the entropy to stay constant. So what's happening now is the gas is expanding, it's doing work. There's no heat flow in or out. So where is the work coming from? The internal energy of the gas, right, is going down, the gas is cooling off. It's doing work and it's cooling. So now this isolated gas cools as it does work by expanding. Oh, I forgot to erase this. And what we've just learned from the entropy being constant is that the final temperature, after the gas expands divided by its initial temperature, is equal to the ratio of the initial volume to the final volume raised to the 2/3 power. That tells us exactly how it cools as it expands doing work. And of course, we still have the ideal gas law holding at all times. Now the temperature is changing while the gas expands, but the pressure is equal to n times temperature divided by volume, and n is fixed. The final pressure divided by the initial pressure is, from the ideal gas law, the ratio of the initial to the final volume times the ratio of the final temperature to the initial temperature, and we know what that is now. So I get V initial over V final times another V initial over V final to the 2/3 power. So this is V initial over V final altogether to the 5/3 power. That's how the pressure changes. And now how much work is done? Well, let's just check that what I said before is correct, that the work is being done at the expense of the internal energy of the gas. The work done is the integral from the initial volume to the final volume of P dV. So we know, I can write it this way, that PV times V to the 2/3 is equal to a constant. I don't know, I'll save a little algebra if I use this little trick. And then if I differentiate that, applying the product rule to PV times V to the 2/3, I can say that dPV, V to the 2/3, plus 2/3 PdV, or sorry, PV, times dV over v, v to the 2/3, is equal to 0. So I just differentiated PV times v to the 2/3 by the product rule. When I differentiated v to the 2/3, I got 2/3 v to the 2/3 minus 1. So now I've got a PdV over here. That was why I did this, because that's what I want to integrate to find the work. What we found is that PdV, if I take that 3/2 and put this over on the other side and multiply by minus 3/2, I have minus 3/2 times d PV. And the reason I wanted to do that is because I can now use the ideal gas law, since PV is equal to n tau. That's the same thing as minus 3/2. And since n is a constant, it's n d tau. So when I integrate PdV to find the work, it's actually equal, the work is equal to minus 3/2 times n, final temperature minus initial temperature. Well, that's, remember, the internal energy is just equal to 3/2 n tau. So that's just the change in the internal energy. So since U is equal to 3/2 n tau, and because we had a minus sign, the work done W is equal to minus the change in the internal energy. The energy to do the work comes from the decrease in the internal energy of the gas as it cools. Question?
Couldn't we have just derived that from like the first law of thermodynamics and saying that d sigma was equal to 0?
Yeah, that's right. But that's sort of what I did, really. But I wanted to, I don't know, why did I do it this way? I think just to see the explicit formulas and that they agree with that general conclusion. Okay. And of course, these changes, which are reversible, are called reversible because we can do what? We can reverse them. And so if I want to change back to the original configuration, I can do so. If I consider reversing the isothermal expansion, I keep the kit system in contact with the reservoir, and I slowly push the piston in. I'm doing work pushing against the pressure of the gas. It stays in contact with the reservoir because I'm doing it very slowly. It stays in the most probable configuration in thermal equilibrium with the reservoir at all times. And the work that I'm doing then winds up where? What happens to all that energy that I put in it goes back to the reservoir, right? So as I push the gas in, I'm doing work. The temperature stays the same. So instead of increasing the internal energy of the gas, which stays the same because it's at the same temperature, there has to be heat flow out of the system back to the reservoir. And therefore, we've completely undone what we did in the expansion step, where we drew heat from the reservoir. We have now put it back. And the entropy of the system and the reservoir are exactly what they were initially. And likewise, in the case of the isentropic expansion, I can undo the expansion by pushing the piston back in while the system remains isolated from the reservoir. Now I'm doing work, and that work is going to do what to the gas? It's going to heat it up. The work that I'm doing is going to add to the internal energy of the gas. There's no heat flow in or out of the system, and return its temperature to what it was initially. So the final configuration is just like the initial one, and we've reversed the effect of the expansion. Okay, and next time maybe I will actually talk about quantum gases. Yeah, I think I will.